Sénégal, cinéma, le Paris. Demain je serai parti. La gare, Dakar, Bamako, Mopti, y a pas de problème, tout va bien. Aujourd'hui je me marie, j'ai confiance. Amour, Solo, Gao, l'Algérie, Tunisie, Italie, y a pas de problème. J'aime au Manhattan, fast food, Dakar, Sénégal, cinéma, le Paris. Ascenseur pour le ghetto, il est minuit à Tokyo, il est 5 heures au Mali. Quelle heure est-il au paradis? Il est minuit à Tokyo, il est 5 heures au Mali. Quelle heure est-il au paradis? C'est au Manhattan, fast food, Dakar, Sénégal, la grand-mère à l'hôpital Dantec, tout va bien, Kairek, moi ici, toi là-bas, le visa au consulat numéro 39, y'attend, à l'état civil, déjà l'an 2000, déjà 2000 ans, au Manhattan, fast food, Dakar, Sénégal, cinéma, le Paris, cinéma, le Paris, il est minuit à Tokyo, il est 5 heures au Mali, quelle heure est-il au paradis? Il est minuit à Tokyo, il est 5 heures au Mali, quelle heure est-il au paradis? Dakar, Bamako, Rio de Janeiro, où est le problème, où est la frontière? Entre les murs, se faufiler dans l'ascenseur, ascenseur pour le ghetto, au Manhattan, fast food, Dakar, Sénégal, cinéma, le Paris. Cinéma, le Paris.
All right, we are on. Welcome, everybody. I hope you can hear me. Those on the private mode, our Substack founding members, welcome. And everyone on the public channels as well, YouTube, LinkedIn. Thank you for showing up today on this very special session. It's the first of 4-part series that we are doing dedicated to the field medals, this year's field medals. Today we'll start more around introducing what the field medals is and some other things, and then we'll jump into our first field medalist that we'll be covering today. And then there will be a follow-up session at some point. We don't have a date yet. It'll probably be on a Friday as well. So stay tuned for that. Follow us on LinkedIn, on Substack, so you can get notified when we start. I'm curious to know where everyone is tuning in from, especially from our Substack members. Yeah, feel free. Okay, I see New York, San Francisco. Okay, well done for make. I believe it's well, not too much early morning, at least in San Francisco. So well done for making it this morning, especially Friday. Anywhere else? Let's see. In Europe, London. Okay. Indonesia, Jakarta. Wow. Well, that's the thing with our community. We are we are spread all across the globe, but united by one common thing, which is mathematics and the applications of mathematics to stuff like AI, quantum computing, cryptography, and so on. So thank you so much for joining. Okay, so I suppose we can get started. Before we get into what the field medals is, maybe a good place to start is to look at another. Okay, I seem to disappear. To look at another prize that you are all familiar with, which is the Nobel Prize. Some of you probably noticed that there isn't a Nobel Prize for mathematics. And this actually, in the early days, created a lot of, well, even today, a lot of speculation to why Alfred Nobel decided to create medals for fundamental science, other fundamental science topics, but excluded mathematics. There are a lot of theories about why. One of them ranging from the fact that he was a very applied person, and at the time, mathematics, obviously, this was mathematics was going through transformation where abstraction was starting to come in. Mathematical structures, all these theories that we know today, like topology, modern differential geometry, functional analysis, abstract algebra, all these things were, already starting to become really shaped into the way we know them today. And so it wasn't clear, I suppose, for someone applied like Mr. Nobel that mathematics would be useful. So that's one of the things. There are also some wild theories, like he didn't like mathematicians. These are all unfounded theories, by the way. For example, one of the mathematicians was going out or something with one of his mistresses or something. But this is all wild, unfounded stuff. I think the consensus in the mathematical community is that it's most likely because he didn't see mathematics as something practical for his liking to include in his awards. And in fact, I think even mathematicians, you might remember this. This is a nice time to share this. Geoffrey Hardy. This is a very interesting book that I recommend you to read called A Mathematician's Apology. In it, somewhere in it, Geoffrey Hardy basically says that he never done anything useful. He's a number theorist, by the way. His primary research field is number theory. So he was basically saying how useless his work is, not knowing a couple of decades later, starting with the works of people like Turing, and then later on Shannon, which was the birth of modern information theory, that number theory would play a very important role in the thing. I have a wide range of applications today, including stuff like cryptography, for instance. So yeah, so naturally, I think you can understand why Mr. Nobel could be excused to not include mathematics at the time because even mathematicians like Hardy couldn't see where the stuff that they were creating could be useful in practical life. To close, I would like to recommend you this this essay. I think you will find it very interesting, by Professor Li Jianji. Why is there no Nobel Prize in mathematics? So if you want to go and take a look at it, I definitely recommend you. Okay, so let's start with what are the field medals? What is the field medals? So I have this poster-like thing that I generated. Okay, so basically, field medals was created after the Canadian mathematician, John Charles Fields, proposed the idea to the International Congress of Mathematics. So the original, according to history, the initial idea for this type of medals to reward mathematicians started in 1923, and then the actual idea, the first awards were given in the 1936, in the 1930s, and the first winners were Lars Allors, he's from Finland, and Jesse Douglas from the United States. So these were the first field medalists. Now, you will probably notice, let me maximize this. I hope you can see, but if not, I can read it for you. The rules of the award are basically, it is awarded every 4 years at the International Congress of Mathematics, and a candidate must not turn 40 before January the 1st of the award year, okay? So I'll comment on this in a minute. Up to 4 medals might be awarded in one cycle. It basically, as you know, it honors outstanding achievement and also future promise, which is why the emphasis on young mathematicians. There are some debates to why this age limit. I'll comment in a minute the downside of it. But I guess some of the consensus that, at least at the time, that was present in the mathematical community was that this idea of mathematics being a young man's game or young person's game, to be more inclusive. So I guess the idea was that mathematicians who are over 40, I don't know what sort of data they have. They probably studied in the past some of the greatest mathematicians and realized that their most productive years were before they were 40. I don't know, but it definitely, indeed, created some sort of discussion about this age limit. And one person that we could say was, unfortunate or casualty of this age limit is this gentleman here, Andrew Wiles. So you probably know this as well. Andrew Wiles, he solved one of the most important problems in mathematics, a problem that has been standing up to that time, I think, for over 300 years. So the Fermat's last theorem. So when he solved it, the next international congress happened, unfortunately, when he was already, I believe, past 40, or he was 40, So anyway, he didn't fall into the age limit of the award, and this actually generated a lot of controversy at the time to highlight, how this age limit thing wasn't really appropriate. In fact, the Congress, the International Congress of Mathematics, I believe they, in the same year or something, or the year after, or the next Congress, I'm not sure well in the historical contest. They created a special medal for him. This brings me to this thing that I recently posted on my LinkedIn, which is this comparison between the Fields medals and the Nobel Prize. I think the general unspoken consensus in the mathematical community is that the Fields medal is not really the equivalent to Nobel Prize in mathematics. Even though we see, I posted this on social media, on LinkedIn, because I've seen a lot of influencers, posting saying, XYZ won the Nobel of mathematics and blah, 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 all this stuff. But the consensus really in the mathematics community is not that the Field medals is equivalent to Nobel Prize. It used to be, when it was the only prize, I'll mention a prize that I think most people in the community think it's much more closer to the Nobel Prize. But at the time, because it was the only historically in the early, before the other prize, which I will mention in a minute, was created, this was the Fields medals was the closest. So naturally, I think at that time, then it would probably make sense more then to say the Fields medals is equivalent to, in a loose sense, to the Nobel Prize. But now it doesn't apply, because we now have this prize. Actually, not that one. That's the Fields medal. Sorry for that. It's this one. It should load. The Abel Prize. So this was established by the Norwegian Academy of Arts and Letters. I think in some countries they call it, they have equivalents. It's like an Academy of Science and Arts, I guess. But this was established in 2002. And in 2003, it was awarded for the first time. So it basically, the rules for it, unlike the Fields medals, it recognizes pioneering scientific achievements in mathematics. Any living mathematician might be nominated. There is no age limit. This is the difference between this and the Fields medal. There's no age limit, right? So the first award went to one of my favorites, living giants, Jean-Pierre Serre. He's a great mathematician. He worked across different important fields of mathematics. In fact, this is one of the reasons why, in his award, they say here, for playing a key role in shaping the modern form of many parts of mathematics, including topology, algebraic geometry, and number theory, and so on. So he was really close to a universalist. He has a huge impact for us, especially in the context of Quantum Formalism Academy, QF Academy, our academy. He's also a great teacher, a great lecturer, a great professor. Not many scientists are great lecturers. This is a fact, but Jean-Pierre Serre, he's a great lecturer. I will play a 2 minutes clip here just to honor him, his teaching style, the way he exposes abstract concepts. And the clip I will play was, I think, about 2 years ago, and he was 97 at the time. And you will see that he doesn't use notes, he doesn't do anything, any of that. He just writes around, very calm, very clear, very concise, with very pedagogical person. So I'll play the clip here just to honor him for his achievements. See?
Elle démarrée par Frobenius, etc. Mais le détail des valeurs, c'est moins fréquent qu'on en parle. Il y a quand même un cas particulier, c'est le cas de la valeur 0. Parce que là, il y a un théorème bien connu de Burnside. Je ne me souviens plus de la date exacte, mais c'est aux environs de 1904. qui dit que si vous avez un groupe fini, un caractère irréductible qui, de G, dont le degré n'est pas 1, degré, il correspond à une représentation de degré au moins 2, alors il a un 0, c'est-à-dire il existe G dans G avec qui de G égale 0. L'article a un joli titre, une propriété arithmétique des racines de l'unité et l'application au caractère. Alors tout à l'heure, nous allons voir dans quel... Enfin, pas tout à l'heure, tout de suite. On va voir dans quel cadre on peut le mettre, qui soit un peu plus général, parce que ça ne fait pas beaucoup de caractères de demander qu'il est irréductible. Si par exemple, votre groupe, c'est le groupe alterné A5, vous avez 5 caractères irréductibles, et en plus, il y en a un qui est égal à 1, alors il ne faut pas. Alors, quelle est la forme un peu plus générale de ce résultat de Burnside? Alors, c'est quelqu'un dont j'ai beaucoup de mal à prononcer le nom. C'est un Ukrainien. Je crois que ça se prononce Smud. Mud comme en anglais Mud, et ça, c'est plus ou moins un S. Ceux qui connaissent l'ukrainien pourront peut-être me dire. Et Smud est un des rares mathématiciens qui est consacré presque toute sa vie justement à des valeurs de caractère. Il a rempli un chapitre entier un traité sur...
Oh, that's it. This is just, I just wanted to share this with you to see how great this man is. Even at 97, he's able to convey ideas, abstract ideas that modern lecturers today, you would be like, reading from paper notes and writing on the chalkboard. But he does it so naturally, and the sense of humor as well. When he was talking about this Ukrainian name thing, he's really a great teacher as well, a great educator, Jean-Pierre Serre. In fact, we at Kiev Academy, this is also a recommendation for you. We always, this is one of the references that we use for anything to do with the linear representations of finite groups. And it's actually, as you can see, it's written by him. We definitely recommend you to, if you are into these things, if you are learning representation theory, for you to pick up his book. If you want to learn a little bit about his life as well, a short expose by my colleague Jack Novak is this ebook here. You can go and download it from our Substack. This is in the context of the Abel Prize. So yeah, I hope you enjoy reading it, and I hope you remember the name is Jean-Pierre Serre. He's one of the greatest. He not just, the other thing I forgot to mention, he's also the youngest Fields medalist in history. He won the Fields medal when he was 27 years old. Okay, and in fact, speaking about this age restriction, for example, a lot of the work that he did later, when he was past 40, the work could themselves be, worth of field medals. So he's really a giant, that we should, cherish while he's here. He's still with us, So I thought this was very interesting to share, and I hope you liked it. So now let's go to our first field medalist that we'll cover today, Mr. Yu Deng. Before I, I can give you a bit of a background about him, and then I'll play a clip trying to expose his work in a more accessible way, and then I will try to comment as after that. I will go over a little bit more, and hopefully you will like that. the stuff that I will share with you after. So he was born in, according to my notes, my research, in Kaifeng, Henan, China, I believe it was in June 1989. And he grew up actually in Shenzhen, okay? As a child, he happens to be very good at Go, playing Go. At one stage, he actually tried to pursue becoming a Go professional, according to what I read in 2001, while he was still in the middle school, he actually competed in the national professional qualification tournament, but unfortunately he narrowly missed it. And this also, I guess it was fortunate for mathematics, because this is where he decided to make the jump to focus on mathematics. So, and wow, few years later, I believe it was in 2006, he won his first prize at the Chinese Mathematical Olympiad. And later, he represented China at the International Mathematical Olympiad, where he won a gold medal at the age of, if I'm not mistaken, at the age of 16. So just to give you a context about his background, he started his university academic journey at the Peking University in 2007. He then transferred to MIT in 2009, graduating with a bachelor's degree in mathematics in 2011, if I'm not mistaken. And this is where, when he was at MIT, he became interested in partial differential equations and worked with Professor Stafilani from MIT on problems involving the nonlinear Schrodinger equation. This will play a role in this work that awarded him the field medals. He then, after he had an stint at Princeton University, where he completed his PhD in 2015 under Alexandru Ionescu. His dissertation, I believe, was the long time behavior of nonlinear dispersive equations. He also received Princeton's, highly regarded, Jacobus Fellowship, right? And after Princeton, it seems like he spent 3 years at the Courant Institute in New York. He then joined the Southern California University in 2018, before moving to the University of Chicago in 2024, becoming a full professor, in last year in 2005. So that's basically a brief overview of his background. He also won other awards apart from field medals, like I believe it's called the Sloan Research Fellowship in 2021, Oberwolfach, I hope this is German, I hope I can pronounce it properly, Prize in 2025, the Clay Research Award in 2026, this year. So that's basically, in a nutshell, his background. So now let me play a bit his intro to his work in an accessible, I believe, engaging way as well, featuring him from the this year's Fields medals. I hope you enjoy, and then I will come back again.
As you watch the waves, you realize it has such a simple, formally simple motion, but realize there's something actually very complicated inside. The question is, how do these simple motions come from these complicated interactions? One of the things that we are interested in is to find patterns within randomness. I usually like to walk close to water, close to the river, the lake, or the forest areas that is close to nature. I tend to be relaxed, and that makes the chance higher to have some real good ideas. I had dreams about math. Sometimes I dream about questions that I actually haven't worked on. I had these dreams when I was writing these papers about legitimate math questions, but in reality I haven't written any of the papers. I'm a professor of mathematics at University of Chicago. I mainly work in the field of PDEs, partial differential equations, and also kind of in connection with probability. The questions I work on mainly concerns how do you see these real-world phenomena like fluids, like waves, from the microscopic pictures of interacting tiny particles. I grew up in Shenzhen in China. When I was in 6th grade, I was working with my dad on a particular question about finding patterns in a particular sequence, and I remember we spent like a few hours together to solve that, and at the end we were really happy that we could solve this question, and that was perhaps the earliest thing I could remember when I get excited about mathematics. I started learning Go when I was maybe about 6. The game of Go is really about analyzing the positions of the board and really having an accurate idea about it before you make your move. In some sense, it was maybe closer to the idea of thinking about mathematical questions and having an idea of the question before you start really working on it. I seriously played it for a few years. I even thought of going for professionals, but in the end I wasn't successful, so I gave up and I turned to the math competitions. I went to the IMO in Slovenia in 2006 and got a gold medal. I started to think maybe I really have some talent in this field and maybe I should really try to pursue this field. Consider a billiard ball. It moves in a straight line, collides with other billiard balls, changing velocity, and keeps moving. Simple. But what if we have trillions of such tiny balls constantly colliding with each other? This is what happens in the hot sphere model of gases, where the little billiards are the gas particles. For such a huge system, it's practically impossible to track each individual particle precisely. Instead, we're interested in the statistical information of the system, overall distribution of the particles, average velocity, and so on. This will be captured in a single density function, which is governed by Boltzmann's kinetic equation. In a parallel picture, consider the water waves, which can be viewed as a system of many wave packets, again constantly interacting with each other. This occurs in the physical phenomena of wave turbulence, where the statistical information is governed by the wave kinetic equation. With collaborators, we successfully justified both scenarios in suitable kinetic limits on mathematical level. The key challenge is that an average particle will experience arbitrarily many collisions and complicate dynamics, as opposed to less than one collision in previous works. To overcome this, we introduced multi-layer diagrams representing the whole collision process and inventing ways to analyze them effectively. These diagrams are enormous in size, but they are formed by the basic building blocks. Each of these basic scenarios, for example, when the billiard ball has one single collision, or when it has one collision that causes a second collision, is easy to estimate. Then, by a carefully designed cutting algorithm, we can break any diagram into such building blocks, which in the end guarantees a complete understanding of the diagrams and leads to the resolution of the full problem. After several thousand years, there are still a lot of mysteries about the universe. Our understanding of the physical universe on the mathematical level is still extremely small. The thing that keeps me in this field is the happiness when your plan works perfectly, that you're able to solve the questions you're faced with.
Okay, I hope you enjoyed that. I think it gave a very concise overview, and also in a very accessible way to Yu Deng's work. I will have some comments, but before that, disclaimer: I'm not an expert on partial differential equations, right? My experience with them comes only from my back in my graduate study days. What I can recommend you is, especially if you are into the technical side of things, on the audience member, you want to go beyond this video introduction, that accessible introduction that you just watched, is to watch this talk. Very interesting, very insightful. In fact, some of the comments that I will be making are mostly based on me watching this and taking some notes, right? So definitely go and watch this, and it's a great presentation about the work of Yu Deng. So most of the things that the few things that I will mention here will be based on this. Okay, so from what I can understand, basically, his field medals was awarded for quite few number of contributions to not just partial differential equations, but also in general to mathematical physics. One of them is the Boltzmann's equation. So as you had a bit of hint of that in the video you just watched. So basically, starting from a large system of hard spheres, moving around, colliding, and so on. What Yu Deng and his collaborators proved is that the Boltzmann equation can be rigorously derived from the underlying particle dynamics for arbitrarily long times, providing the Boltzmann solution exists over that interval. Earlier results before he and his collaborator, I will actually mention that towards the end. Earlier results had largely been restricted, from what I understand, to short times, because effects such as recollision, stuff like recollisions, become increasingly difficult to control, as you can imagine. So that's one aspect of his work. The second aspect of his work, from what I understand, is about wave kinetic equations. Here you can picture interacting particles with weak interacting waves. Yu Deng and his collaborators, they basically rigorously, from what I understand, derived the 4-wave kinetic equation from nonlinear dispersive dynamics at the correct kinetic timescale, and extended the result to arbitrarily long times under the corresponding assumption, existence assumption. So he also made contributions to nonlinear Schrödinger equations with the random initial data, I would say. Together, he and his collaborators, I will emphasize this towards the end, why mathematics, even the greatest like Yu Deng, they are not lone wolves, right? They work with the collaborators. In fact, well, I'll mention it now. One of his collaborators in his most impactful papers, if you look at this, watch this this talk by this professor honoring Yu Deng, you will see that he co-authored it with a mathematician, that's Hani, And so even though Yu Deng has been awarded to him, this shows that great mathematicians, very often they need other mathematicians, to help them basically succeed. This also happened with Andrew Wiles when he was working on the Fermat's last theorem, because he needed other expertise in different fields of mathematics, I believe stuff like automorphic forms and so on. So he had to enlist other mathematicians. I think one of them is Richard Taylor, who helped him in his journey to solve the problem. So just to emphasize this aspect, modern mathematics, you hardly have some sort of lone wolf genius doing everything by themselves. It's generally very collaborative, and because mathematics is so specialized across multiple fields, sometimes you might have a feeling that whatever you are trying to solve needs another field of mathematics that you are not expert on, and then you draw another mathematician from that particular branch of mathematics to help you. So this is actually a great example of how collaborative work can really pay off in the case of Yu Deng's work. The other thing, I suppose, is I always like to think about the impact. So because he's dealing with the partial differential equations, what I did was to email some people working in applications that I'm interested in, for example, that I'm curious about, stuff like physics-informed neural networks, for instance. So I emailed one person asking, the person also wasn't aware of Hani's work, but because of the field methods, because obviously they in pins, you need the partial differential equation. So he went and looked at it. So I won't name him because this is a speculative. I call it a speculative potential application or impact of Yu Deng's work. So basically, this person told me this. They got back to me on this. So I won't name them because this is speculation. So what they told me is that there could be some potential applications in long time PDE learning. Why? Is because apparently, according to him, one of the recurring difficulties, with pins is that small residual does not necessarily guarantee that the learned solution stays close to the true solution over long time intervals, especially when you are dealing with nonlinear or multi-scale PDEs. So Deng's work is therefore, because it's concerned about controlling nonlinear dynamics over time, very useful for this. The other thing that this person told me is that random initial data and low regularity solutions also is another area where the work of Yu Deng could be very, very useful. What he said was standard pins, pins standing for physics-informed neural networks, are usually most comfortable when solutions and derivatives are sufficiently smooth because the PDE residual is evaluated through differentiation of the neural network. So from his point of view, Yu Deng's probabilistics PAD work deals precisely with this type of regimes where typical initial data might be extremely rough, right? Especially for like a real world messy data, right? And where deterministic notions of regularity are not sufficient. So just to give you a bit of flavor, so this is something that I thought I would share with you. As it's put there on the bracket, this is speculative. It was just my curiosity to see, okay, let's look at the potential impact or applications that this works, since he's working on PDEs. PDEs are a natural thing for pins. So yeah, I hope you enjoy this. There was something else I forgot to include here, but you can find it on YouTube, which is his advice to young mathematicians You can find that on the YouTube playlist of the Congress. But yeah, that's it I have to share with you. I hope you enjoyed it, and yeah, feel free to type in on the chat if you have any questions. If you don't have any questions right now, you can always email me. So I'll give you maybe 30 seconds or so to see if you can start putting the questions. If not, we can leave it here because I know it's Friday. You might have a lot of things on your plate. So yeah, especially those in the US, because you woke up early. You might be about to start your work, even if you are doing remote work. So I don't want to get hold of you for too long. So yeah, leave your comments. And if you have any questions, I'll wait here for 30 seconds or 40 to see. Okay, we have a question. This is in respect to the speculation that I just made. Is how could this work influence scientific machine learning or PINs in the future? Well, that's exactly what I was just speculating about, based on the thing that this person got back to me, is that the current his analysis was that long time PDE behavior, rough initial data and multi-scale limits could eventually inform how physics-informed models handle long-time stability, I guess also probabilistic solutions and transition between, both the microscopic and between the microscopic and effective PDE descriptions. So that's the best I can say here. Again, this is speculation. Yeah, but thank you for the question anyway. Yeah, you're welcome. Yeah, it's really interesting. I mean, this is one of the reasons why I reached out to this person, because PDEs has so much applications, and people nowadays talk about physical AI, world models, and all these stuff. Underpinning all this is really pins. So yeah. Let's see. Any other questions from the, especially from the public channels? Here's a very interesting question as well. I'm not sure if I can, let's see, let me try my best to answer it. So the question says, let me read it for you. Unfortunately, I can't show you the questions on the thing because of privacy. I don't know if this person who asked this question want to see themselves on the thing, even though it's an interesting question. So, so the question is, how is this connected to Hilbert's sixth problem? That's a very interesting question indeed. I actually saw that. I suppose after I actually went through, because there was a mention of the Hilbert's sixth problem in one of the blog posts or something. So one of the things that I could get from reading that was that one part of Hilbert's sixth problem asks for a rigorous mathematical connection between microscopic mechanical laws and macroscopic continuum equations. So I guess we can say that, Yu Deng's work basically provides a good step in this direction by connecting, for example, what you saw in the thing, hinted at the video clip that he showed, sphere dynamics to the, say, Boltzmann equation. So that's basically as far as I can think. I can just think of on top of my head based on what I read. Yeah, but thank you for the question. There is also another question here. This to do with the probability. What role does probability play in his work? Looking at it again, that's why I definitely reference you to go and check this talk here, because this has more details, especially in your case. You are more of I know you are more technically leaning community member, but I believe probability is one of the key things on his work in respect to nonlinear Schrodinger equations. Typical initial data, for example, sampled from what I guess physicists they call Gibbs type measures, can be extremely irregular, and sometimes from just watching this talk, it seems like sometimes that so irregular that they are some sort of a distribution than really ordinary functions. Okay, so this is what I could get from watching this talk and also reading some blog posts about Yu Deng's work. Anything else I cannot say. As I said in the disclaimer, I'm not an expert in PDEs, even though I had PDEs during my student days, graduate level thing, but no way at research level that, Yu Deng and the current people working in the field are. Okay, so any more questions? No? Okay, in that case, we leave it here. I hope you enjoyed it, and follow us on LinkedIn, on Substack, subscribe to our Substack so you can get notified when the next session for our second field medalist will be done. But yeah, I hope you enjoyed this introduction. Right, we started off giving some sort of historical context about field medals, and then we went into Yu Deng's work. So yeah, thank you so much for showing up, and I'll see you next time. Have a great day wherever you are, in particular our American audience. Thank you so much for waking up this early, and have a wonderful Friday. I'll see you next time.